Hello and welcome. In this video, we're going to take a look at some really basic shortcuts for finding the derivative of common functions. This is kind of the video or the section that everybody's been waiting for, even if you didn't know you were waiting for it. We've been looking at limits, trying to find out how to find the derivative of a function using the limit definition, but now we're ready to take that definition and apply it to some common functions and come up with several shortcuts so that we can bypass having to worry about the limit for common functions. So let's take a look at a couple examples. Remember that the definition of a function is f prime of x is the limit of f of x plus h minus f of x all over h as h goes to 0, provided that the limit exists. And remember that some functions are not differentiable everywhere. Let's take a look at some basic differentiation rules, starting with what we call the constant function rule. Let's suppose that f of x is equal to c. Now, applying this rule, we would say that the derivative of f would be equal to the limit, as h goes to 0, of f of x plus h minus f of x. But since the function is just a constant, it's just some value c, f of x plus h is simply just c, and f of x is simply just c. And we end up with the limit of c minus c divided by h. Now we're trying to take the limit as h goes to 0, and we can't do that, but we do notice that the numerator is always going to be equal to 0. And that means we're left with 0 divided by h, which is always equal to 0 for any values of h close to 0. And so we end up taking the limit as h goes to 0 of just 0. And so the derivative is 0. Now we should write this out as a more formal rule. The derivative of some constant is equal to 0. Or rather, differentiating a constant is equal to 0. And that should make some amount of sense, since a derivative represents the rate of change of a value, and a constant is a value that never changes. Its rate of change is equal to 0. All right, now for the one big rule that we're going to be using frequently from here on out. Because our first major kind of function we might want to talk about is a polynomial, and that involves powers of x. So what if we have a function that is a power of x? We need something called the power rule. Now, for the power rule, we'll assume that a function is simply just x to some power n. Using the limit definition, f prime of x will just be equal to the limit, taking as h goes to 0, of x plus h to the power n minus x to the power n, all divided by h. We've done a few examples like this, maybe with x squared or x cubed, and the strategy was the same. We need to expand out that binomial x plus h to the power. And once we do that, then we can collect terms and hopefully factor and simplify. But let's try to find a way to do this in general. And it helps to know the binomial theorem. There's a common way that we can find out how to expand x plus h to the power n, whether that's squared, cubed, or to the fourth power. But there is a bit of a pattern here, so let's take a look and see what happens. Let's start off with the most basic power, n equals 0. X plus h to the 0 is simply equal to 1. Well, if we have x plus h to the power 1, then that is simply just x plus h. And we probably know a shortcut for squaring x plus h. That would be x squared plus 2xh plus h squared. And we may even know a shortcut for cubing, and that would be x cubed plus 3x squared h plus 3xh squared plus h cubed. But is there a pattern in general? Well, let's take a look at the coefficients here. I've highlighted all of the coefficients in red, and any of the coefficients that are 1 I've now also included. And there is this beautiful pattern known as Pascal's triangle. And you can see a triangular shape where we have 1s along the edges. Now, to get each new entry in the lower row, such as the 2 here, we can just simply add the values above and left and above and right. 1 plus 1 gives us 2. And another row down, how do we get this 3? Well, 3 is simply just summing up 1 and 2. If we were to continue this pattern, we would also see that x plus h to the power 4 had similar coefficients. Starting with the highest power, x to the 4, will have a coefficient of 1. And there's always 1s along the edges. Our next term, power of x reduces by 1, and the power of h increases by 1. Now the coefficient here is simply going to be 1 plus 3, and that's going to give us a coefficient of 4. In our next term, we'll increase the power of h by 1 and decrease the power of x by 1. Now we have an x squared h squared. 3 plus 3 gives us our coefficient of 6. In our next term, we'll have only a single x, but it will have an h cubed. Coefficient of 3 plus 1, which is 4. And finally, we will just have an h to the power 4 with a coefficient of 1. And this pattern will continue on and on. Now, as we've done this expansion, remember that we are always going to be subtracting x to the power n. And that is the only term in the expansion that does not have something with an h in it. So after expanding the binomial, when we subtract x to the n, it will always cancel out this first term. The good news is, once that first term is canceled, all of the remaining terms have a factor of h, and those can be canceled. We have an h in the denominator, and that will cancel a single h out of all of the remaining terms in the numerator. So let's see if we can write out the expansion of x plus h to the power n in more of a general form. The first term of the expansion is always going to be x to the power n. The second term is always going to have a power of x that is 1 less than that. So we will have an x to the power n minus 1. We're also going to have a single h in the next term. And the coefficient, we can see a nice pattern. 1, 2, 3, 4. It is simply just equal to n. Now we will have additional terms afterwards, and they will all have some h in them until we get down to the last couple terms. And if we look at the second to last term, we'll have just a single x, and our power of h is going to be 1 less than n. The coefficient of that term is also going to be n, because if we take a look at the last term, we also see the same pattern, 1, 2, 3, 4. And the very last term is simply going to be h to the power n. Now all of that, we're subtracting x to the n. So we can see the x to the n's cancel, and we have an h in every remaining term that will cancel the h in the denominator. When we cancel the h, every one of the h's is going to be reduced by 1. And then you can see we have one term where there is no more h's, and that is our nx to the n minus 1. All of the remaining terms will still have h's. But since h is approaching 0, we will only end up with one term remaining, the n x to the n minus 1 term. The remaining terms are simply going to be a boatload of zeros added together. As h goes to 0, we can see all of them are getting smaller and smaller, and the only term that is remaining was the term where the h canceled out, nx to the n minus 1. And there is our power rule. All of this work so that we can shortcut it later and just say that the derivative of x to the power n is equal to n times x to the n minus 1. Now, we've only seen this rule for positive integers. So x plus 1 to the 0, 1, 2, 3, and 4, and other positive integers. It's a little bit harder to prove, but this works for any real number n. Well, now that we know how to look for derivatives of constants and derivatives of powers, we start to get the idea about how to find the derivative of a polynomial. But polynomials have powers of x's with coefficients in front of them, so we're not done yet. We also need to know how to take the derivative of some constant, some coefficient in front of a power or function of x. And that leads us to the constant multiple rule. Let's suppose we have a function g of x, which is just a constant multiple of some other function f of x. Then using the limit definition, g prime of x would just be equal to the limit as h goes to 0 of g of x plus h, but g of x plus h is simply c times f of x plus h minus g of x, which is c times f of x, all divided by h. But you can see that there's a nice common factor of c across the numerator. And if we factor c out of the numerator, and in fact, factor c right out of the rational expression, we can take that c and use a property of limits. We have a constant multiple rule for limits, and that allows us to take the limit of the function inside and multiply the result by c. That leaves us with c times the limit as h goes to 0 of f of x plus h minus f of x all over h. And this is simply the definition of f prime of x. So g prime of x is simply c times f prime of x. And that leaves us with the constant multiple rule. If we differentiate a constant multiple of a function, it is equal to that constant multiple of the derivative of the function. Now, we're nearly able to take the derivative of a polynomial. But a polynomial isn't just a power of x with a coefficient. It can have many different terms. We can have a cubic term plus a linear term plus constants, and we can have all of these added or subtracted. We need one more rule before we can look at derivatives of polynomials with super quick efficiency and no limits to worry about. And the last one we have to look for is the sum and difference rules. Okay, well, how do we take the derivative of two functions added or subtracted? Why don't we first start off by thinking about addition? So the example here would be if we want to find the derivative of, let's say, f of x plus g of x. By the definition of the derivative, we take the limit as h goes to 0. Now our function is actually f of x plus g of x. So if we evaluate that function at x plus h, we'll end up with f of x plus h plus g of x plus h. Then we subtract the function evaluated at x, which is just f of x plus g of x. The entire expression is then divided by h, and we have to evaluate this limit. Now we can do a little bit of manipulation with fractions here. Maybe we have to rearrange some terms first. We can put all of the f's as terms together, making sure that we subtract f of x since it's got a negative sign in front of the square bracket. And then we can put the g terms near the end. Again, making sure we have minus g of x since it is being subtracted. Now, all of these terms are over a common denominator. So it makes just as much sense, if I wanted to split up fractions and have two fractions over a common denominator as well. Now, the limit would apply to the entire expression, but I've just split up one fraction into two. Now, property of limits again is going to help us out here. There is an addition and subtraction property for limits. One of the limit laws will allow us to apply the limit to each of the individual terms. We can take the limit of f of x plus h minus f of x all over h, and we can apply the same limit as h goes to 0 of g of x plus h minus g of x also all over h. And these two separate limits are exactly the definitions of f prime of x and g prime of x. So that is how we can look at the sum of two functions and find the derivative. And I'd leave it to you as a little exercise to try the same thing with f of x minus g of x. It's almost the exact same set of rules that you're going to be needing to apply. You just have to be a little bit more careful with negative signs. We'll find out that as a result, that if we want to take the derivative of f of x plus g of x, it is simply just f prime of x plus g prime of x. And if we wish to subtract f of x minus g of x, we'll end up with f prime of x minus g prime of x. So it makes a lot of sense to use this plus minus symbol. Plus minus symbol can mean plus or minus, a sum or a difference depending on what you have. And now we can take constants, powers of x, constant multiples, and sums and differences in order to construct a polynomial. And then we can find the derivative of polynomials very quickly. Let's see how we can do that. Okay, here we have a polynomial, which is degree 5, highest power being degree 5. Let's evaluate the derivative, and we won't even have to write limit down once. So we can start off with the fact that f prime of x means that we're differentiating all of the function. Now, the first rule that we're going to apply here is the fact that we can split up addition and subtraction into separate derivatives. So initially, we'll just write out every one of these steps. We're going to differentiate x to the 5. We're going to differentiate 4x cubed and subtract that from the derivative of x to the 5. And then we'll take the derivative of 2 and add that on. So that is using our sum and difference rules. Now, the first differentiation operation is taking the derivative of x to the 5. We can use the power rule. The derivative of x to the 5, since n is 5, is just going to be 5 times x to the power 4. You can think of the power rule as simply just taking the exponent, dropping it in front, and reducing the power by 1. Now, the second term has a power, but we can't really deal with that power rule until we deal with the constant in front. And this is a 4, which is a constant multiple. It's a coefficient. So I'm going to write this step out. We will probably skip this in the future, but I'll show you that the 4 can then be moved out front using the constant multiple rule. And from there, we can do our derivative of x cubed in a further step. Last but not least, we have the derivative of 2. And that is simply a constant. Now, it's the derivative of a constant, not the derivative of a constant multiple. Constants are unchanging numbers, so their rate of change is 0. Okay, now I only have one remaining differentiation operator. I just have to take the derivative of x cubed, and I will have finished all of the differentiating steps. And this time, I can use the power rule, and with n equal 3, I will just end up with 3x squared. Now, don't forget that this 4 still needs to be multiplied by 3x squared. Now, it doesn't make a lot of sense to always write plus 0, but it does help when we're just getting used to derivatives to see what happened to that term. It doesn't make a lot of sense to just say it disappears. It makes more sense to say the rate of change of that term is 0. And now we can simplify. Our final solution, our final answer, f prime of x is equal to 5x to the power 4 minus 12x squared. We don't have to write that plus 0 in the final step, but we all know that that 2 just has a rate of change of 0. Now, of course, I did mention that the power rule is not just for positive integers. It can be for any real number. So let's just do another example here where we can take it a little bit outside of the normal, not just a polynomial, but we can throw in roots or rational exponents. Okay, here's another function, f of x. And this time we've got roots, we've got rational exponents, and we also have a rational expression 5 over x. And before you get started, it helps to try to write everything in terms of powers. So rather than jumping right into differentiating every term, let's start by rewriting root x as x to the power 1/2. And let's rewrite 5 over x as 5x to the minus 1. Now it's a little easier to see that all of the x's are simply powers, and we have constant multiples, and we have terms added together. So we're ready to start with the derivative. And this time around, we can start to think about the rules without having to write every one of them down. We'll start to get a little bit quicker at this. So 4 is a constant multiple, and it is going to stay put. And then we need the derivative of x to the 1/2. Now, remember that the 1/2 comes down in front of the x, and then we subtract 1 from the exponent. The half minus 1 is negative 1/2. We have a term, and we'll add the next term. 5 is a constant multiple, so it will stay out front of the differentiation operator, and then we will take the derivative of x to the minus 1. Now, because we have a negative power, the negative 1 comes down in front of the x, and when we reduce the power by 1, it'll drop to negative 2. And finally, our third term has no constant multiple in front, so we just get straight to the power rule. The derivative of x to the 1/3 means we'll have 1/3 x to the minus 2/3, since the power has to drop by 1. And then we'll simplify. The derivative f prime of x can be written out a little nicer. 4 times a half is 2. X to the 1/2 can be written as 1 over the root of x. And we'll see a 5 times the negative 1 leaves us with minus 5, and x to the minus 2 can be written as 1 over x squared. Plus 1/3, and we can write x to the negative 2/3 as x to the 2/3 in the denominator. And you'll notice there is some interesting behavior about what values of x we're going to be able to plug into this derivative. It's sometimes the case that a function is defined for a certain x, but its derivative is not defined. And that means that we can have a function that is defined at a certain value, but not differentiable. So that is something that we can take a look at in future videos. So I hope this has really helped to be able to get the derivative of some basic functions super quickly. We don't have to deal with limits every single time. But that's not to say that limits are over and done with. Every one of these rules comes from the limit definition of the derivative, and you need to understand how they are coming about. In the future, there's going to be some other functions that are a lot trickier to explain their derivatives, but they still are all to do with limits. So we'll save that for future. Thanks for watching. I'll see you in the next video.